Okay, so the work that I want to present today focuses on developing a computational tool that allows designers to explore for design inspiration within pattern database. And today I will first go over methodologies for creating the design tool. And also I will present cognitive study that validates the efficacy of the tool in design practice. Okay, so, all right. So I want to begin my presentation with a short story of how Dyson vacuum cleaner was invented. So here is a picture of the vacuum cleaner. It looks nice, it's powerful, but one thing that makes Dyson so famous is that it's the world's first bagless vacuum cleaner. So I remember when I was a kid, vacuum cleaner used to have dust bags. And when the bag is full of dust, we had to remove it. Otherwise, the dust clogged in the bag causes vacuum cleaner to lose suction. So Dyson, the founder of the company, thought that it was a design problem. So he came up with thousands of prototypes later and invented a vacuum cleaner without a bag. And this idea was actually inspired by other design, and that design is the cyclone tower. So cyclone towers are usually found in factories, and it's used to separate waste particles like paint particles from the air using the centrifugal force. So this approach that Dyson used is called design by analogy, short for DBA, and involves retrieving information or knowledge from one's memory or from other existing design solutions. We call that a source domain. Then we transfer that information to one's engineering design problem, and we call that a target domain. And many innovations were resulted from DBA. Examples include Nike's shoe shock absorption technology, inspired by Formula One racing shock observers. BMW's in-car communication system, inspired by video game technology. And a device that detects urinary tract infection, inspired by a fidget spinner. So DBA is a tool for innovation, for engineering design and product development process. The question is, where can we get that information or knowledge that can be transferred to our design problem? Well, many DBA researchers chose the pattern database as a source of analogical inspiration. It is large and growing design repository. It contains designs that are patented, meaning that they are novel, non-obvious, and industrially applicable. And patents are structurally well-formed, and it has abstract description and claims that contain the embedded design information. And it uses a standard classification system, and one of them is called CPC, that systematically categorizes patents by their fields of application. So for these reasons, patent database is not only an attractive source of innovation, but also an efficient means for retrieving analogies. Well, there has been much effort to computationally support the design by analogy using pattern database as the source of inspiration. But many of the design by analogy tools to date use a query-based search, meaning that it requires user to input keyword or query function in the tool to retrieve a set of stimuli. And those stimuli are determined by the query algorithms. So using keywords to retrieve a stimuli is efficient. It basically dominates the market. However, if designers don't know what queries to use, or if they lack experience with a design tool, the designers may not retrieve the right stimuli that they are looking for, and it is likely that they will attempt trial and error techniques until they get the right queries. And my research work started from the idea that retrieving analogies can be done in more designer-controlled manner. Instead of using only keywords to search for analogies, we can visually and interactively explore a space of analogies. Imagine that you are in a library surrounded by different books. If you can explore a space of analogies like you do in the library, you have the potential to discover more useful and unexpected analogies. And a design tool that supports this kind of interaction can be more intuitive and thorough for the analogical retrieval process. So that was my motivation for this work. And the work that I want to present today can be divided into three separate studies. So the first study is about discovering a structure of pattern data. The second study is about creating an interactive data visualization tool using the result from the first study. And the last study is about validating the efficacy of the tool by conducting cognitive engineering design study. So let's begin with creating a structure in pattern data. Discovering a structural form of data is essential for providing valuable insights into the meaning of and relation among data. For instance, Linnaeus's tree structure for biological species and Mendeleev's periodic table led to major scientific advancements in understanding nature. Finding a structure in data often requires clustering or categorization of data, and a computational method that can automatically classify various patterns into common topics can be useful for creating a structural form of those patterns. In text mining field, methods were developed to manage large document archives, and tools have been developed to classify documents into categories, identify common themes, and help users find relevant text as illustrated by this figure. Since all pattern designs are archived in document format, we can use a topping modeling method to process a random set of documents and group them into different categories. And by clustering the documents based on their topic similarity, we can create a pattern structure. The topping modeling method clusters patterns by their topics, but also it can be used to understand what those topics are. So in category 1, these documents have the shared topic of red, apple, strawberry, and so on. And in category 2, the second category has a shared topic of yellow, banana, lemon, and so on. And generally, the labels of the cluster is a set of words that best describe the topic. And this can be all determined from a topping modeling method. All right. So we can use the topping modeling to create a pattern structure and use the structure to search analogical inspiration. But designers often have diverse objectives. They have different lenses through which they look when exploring for inspiration. For example, designers may ask themselves, like, what functions does the technology achieve? What components were used? How the technology behave, and what principle does the technology rely in order to work? And I believe that if we give these different lenses to the designers or different ways to view the pattern structure, they may have the ability to explore the structure in a more tailored and efficient manner than simply exploring the same structure that is made for all. So here we decided to use the 4 lenses to affect the way the patterns are structured. The first one is about function. And here, only verbs in the pattern documents were used to create the function-based pattern structure. And this is a practice that is done by other text mining researchers. For the component lens, we manually compiled a list of words that characterize components of different technologies. Then we performed the text mining, the topping modeling on documents that only contain the component words. For creating the behavior-based pattern structure, we used a list of behavior words that were manually compiled. For engineering principle-based pattern structure, we used words extracted from a glossary of engineering. Then we performed the topping modeling. So basically, by applying these 4 lenses on the pattern structure, we created 4 different representations of a single pattern structure. And I will show you the 4 different representations as I do the demo of the tool in the next study. The next step is turning the pattern structure into an interactive data visualization so that designers can explore the different patterns for analogical inspiration. And here I want to show you how we visualized a pattern network using the topping modeling result from the first study. So in the first study, we created a clustering structure of patterns. And individual patterns are characterized by a clustering label. The clustering labels were composed of 5 words that best describe the topic of the clustered patterns. So we have a table here that shows that pattern 1 is described by words 1, 2, 3, 4, 5. Pattern 2 is described by words 1, 3, 5, 7, and 9. And pattern 3 is described by words 2, 4, 6, 8, 10. We can create a simple network between the patent and its clustering label. For example, we can create a node that represents the patent and connect it to 5 nodes that represent words that describe this patent. Then we can do the same thing for other patents, but adding them on an existing network. So we have patent 2, and we have words 7 and 9 connecting to patent 2. We have patent 3 here, and we connected words 6, 8, 10 to the patent 3. So this becomes a network of 3 patents. And I did this with 500 patents here. So here's the snapshot of the tool. The name of this tool is called Vision. And now I will switch over to the tool to show you how this can be done. How this can be used. So I hope you can see the tool here. Yes. Okay. So yeah, this is a vision tool. The individual, the round nodes, they represent patents. So if you hover over it, you will see the title of the patent and followed by their patent ID number. And if you click on this patent node, you will actually see that this is connected to 5 labels or 5 topic words. So this here, the screwdriver for rotisserie is connected to gear, motor, shaft, wall, mount. So these labels describe what this patent is about. It supports basic user interactive activity. So you can zoom in, zoom out, move around the structure. And here also you will see some filtering functionalities. Okay, so let's do some kind of case study here. So let's assume that we are designers and we want to design a nutcracker, a device for cracking nuts. So we can just dive into this structure and look for patterns that are related to nut cracking mechanism to get some inspiration. But since this has it has 500 patents and a lot of nodes are here, so it's very hard to explore this structure. So what I can do is I can uncheck all to start from the scratch. And then I can go through these label words or the topic words that can be used to, or that is related to the nut cracking mechanism. So here I see blade, so I can enable this checkbox. And let me check some words here. Maybe you can use clamp to crack nuts, that can work. Compressor, yep. What else? Jaw, yes, knife, that can work. And let me just click one more, and I think that's enough. Razor, yep. So we have a reduced pattern structure, and I think it's easier to explore this structure. So let me let's explore this structure over here. So this is these patterns are all connected to blade, razor, or knife. And if I hover over this, I see some patterns that are related to these topics. And I see a paper shredding roller assembly, and I'm actually interested in seeing what this pattern is about. You can click on this pattern to open the pattern document. And from here, you can read the abstract to learn what this pattern is about. I'm more a graphic visual person, so I can click on the image to see what this is about. And one idea that comes to my mind is that we can maybe use the paper shredding component to crack nuts. I don't know how well that works without damaging the inside of the nut, but it's definitely an idea, an initial idea. We can make it feasible as we develop this idea and improve on it. So that's how basically you explore this pattern structure to get some inspiration for my design problem. And one thing that I want to show you here are these 4 buttons over here. So if you click on this button, the component button, this will structure the patterns by their components. And the words or the topics that you see over here are all component related words. And that this is actually related to the lenses that I talked about in my first study. And if you click on the behavior button, this will structure the patterns by their behaviors. And these are the topic words that are related to behaviors or adjectives or words that that characterize how devices behave. This is engineering principle, and this is function. Function is basically the verbs in the documents, and that's how we basically create different representations of pattern structure, and it's created to give them more control over over this design, over this pattern structure. Okay, now let's go back to this slide. Okay, so there was the vision tool, and now in the next study, we validated the effectiveness of the vision tool in a conceptual design process. And here we conducted a cognitive engineering design study, and it was done in a controlled lab setting. Okay, so 26 students participated in this study. 21 were grad students, 5 were undergrad students, 25 were mechanical engineering students, 1 was aerospace engineering student, and they had 2.5 average years of experience in design related or course or industry. These students were assigned to 2 conditions. 15 were assigned to vision condition and 11 were assigned to Google patent condition. Here, the first group used the vision tool, the exploration-based approach to retrieve patterns and use that to generate ideas. The second group used the Google patent, the query-based approach, using the keywords to find patterns, to retrieve patterns and use that to generate ideas. The objective of the study was to evaluate how the vision tool and Google patent affect the design outcomes and the pattern retrieval during the idea generation process. This diagram shows how the study was conducted. They were given a task to design a device that used human motion to generate electricity. So human motion electricity generator, or yeah. So the participants worked for 15 minutes individually on this design problem without using any design tool. So no design tool was given during the first idea generation. After the first idea generation, participants were given a 10-minute teaching session. And those in the vision condition learned how to use the vision tool to retrieve patterns and use that to generate ideas. And those in the Google patent condition learned how to use the Google patent to search patterns and use that to generate ideas. And during the teaching session, they were provided laptop computers so they can practice using the tool. After the participants expressed that they were confident using the tool, they were proceeded to the second idea generation. And this time, they used the provided design tool to retrieve patterns and generate ideas for the same design problem. And during the second idea generation, the computer screens were recorded with their permission for the data analysis purpose. And the study ended with a 10-minute survey to gather their demographic information and understand their user experiences with a vision tool or Google patent. Okay. So participants generated ideas in form of sketch, text, or combination of both. And the ideas were analyzed by their quantity, quality, and novelty. And here, actually, I want to show you some examples that were from the participants. So this is actually a soccer ball with a capacitance inside it. So as you kick it, it will collect energy from that impact. And this idea is actually an exoskeleton device that you wear on your knees. So as you walk or run, it will collect energy from that human motion, and the energy will be stored in this backpack. So this is some examples of the ideas that the participants generated. And again, these ideas were analyzed by their quantity, quality, and novelty. These metrics are widely used in the engineering design research field. Okay. So for the quantity of ideas, we only analyzed the ideas in the second ideation phase. So here we found that there was no significant difference between the Bayesian condition and Google patent condition. Most participants generated 1 or 2 ideas during the second idea generation phase. The second metric, quality, was used to determine how well the generated ideas meet the design requirements defined in the problem statement. So we had a set of design requirements, and we computed how well each idea meets these requirements. And here's the result for the quality. So for the quality of ideas, we found that there was no significant difference between the Bayesian condition and Google patent condition in the second idea generation phase. But we found that the quality of ideas significantly decreased when they were given the design tool. And this was not expected, and I will discuss more about it in the discussion slide. The third metric, novelty, was used to determine whether the ideas were unusual within a space of possible solutions. So this metric measures the novelty. So if many participants generated the same design problem, the solution receives low novelty score. And if only one participant generates the design solution, the solution receives high novelty score. That's what it measures. And here's the novelty result. And here I again found that there was no significant difference between the Bayesian condition and Google patent condition in the second idea generation phase. But I found that the novelty of ideas increased significantly when they were provided either the Bayesian tool or the Google patent. In addition to the design metrics, we also measured the level of similarity between the generated ideas and retrieved patterns. In other words, we measured the degree to which participants directly copy an example design when generating ideas. And this graph shows that out of 12 ideas that were generated in the Bayesian condition, 3 were directly similar to the retrieved patterns. But for Google patent condition, out of 20 ideas that were generated, 15 were directly similar to the retrieved patterns. And participants in Google patent condition copied the patent designs significantly more than did participants in the Bayesian condition. Now, I want to discuss about the findings from the study. So the first discussion point is that the quality of ideas decreased, but the novelty increased when the participants were given the tool for retrieving patterns. The diminished quality was not expected. One possible explanation is that searching patterns and navigating the tool can cause high cognitive load that distracts designers during the idea generation process. And we analyzed the video data, which was the screen captured during the study, and we noticed that some participants spent too much time on retrieving or searching patterns. On the other hand, the novelty of ideas increased using the Bayesian tool or Google patent. This means that they were able to generate solutions that were more uncommon within the design solution space. So taking this all together, we can see that both Bayesian tool and Google patent help designers to generate new and bold ideas. The second discussion point is that Google patent resulted in ideas that directly copied the patent designs. And to understand why there was such difference between the two conditions, I created word clouds that represent the keywords that were used in the Bayesian tool and Google patent. So this word cloud is from the Google patent condition. For Google patent, the keywords that were frequently used were the words from the design problem statement, like human, motion, energy, generation, and power. And using this set of keywords, participants were only able to retrieve patterns that are very similar to already existing design solutions. Examples are shown here. So these are the images from the patterns that they retrieved. And these are the drawings or the ideas that the participants generated. And this finding was consistent with other prior studies that for novice designers, examples that are similar to existing design solutions hinder their abilities to produce original ideas. And other studies showed that novice designers are likely to copy the design because reusing designs that are already certified reduces the risks involved in the idea generation process. So that could be the reason why participants in Google patent condition retrieved existing design solutions and generated ideas that are similar to those solutions. And this is a word cloud from the vision condition, also made with top 50 keywords. Here we can see that the participants used various keywords when exploring for patterns, and some of the words didn't directly come from the problem statement. And this implies that they discovered different words as they explored the pattern network in the vision tool. And comparing this word cloud with that of Google Pattern, we saw that using the query-based method, it can be difficult for novice designers to come up with different queries because many of them do not have the experience to retrieve examples from other technological domains. On the other hand, the vision tool allowed the designers to explore different patterns, different analogies in various domains. And this could be helpful in generating ideas that are not directly similar to pattern designs. Limitations that I want to mention in my work is that the cognitive study was done with the engineering students. So we could gather more data if we could conduct a study with the more expert designers who have different expertise levels. Other limitation is that the vision tool currently contains about 500 patterns, which is very small scale compared to the millions of patterns that are available in database. And this limits the tool's ability to provide various analogies. So we hope to scale up the size of the database. Some future study includes the improvement of the user interaction support that helps designers to interact with the tool. More visualization styles can be developed to give designers more options for each visualization to work with. Lenses can be created to represent the pattern network differently. And lastly, the vision tool currently uses only pattern data, but it could use biological systems as the source of inspiration. And that could assist designers in practicing biologically inspired design. So that's it for my presentation. Thank you for listening to this presentation, and I will be happy to answer your question.